Hello everyone, this is Wang from Shanghai Jiao University. Here I'm going to present this paper from ATC 2022. The title is Zero Overhead Monitoring for Cloud Native Infrastructure using RDMA. This work is done during I'm a research intern at Alibaba Cloud. Here is the outline of my presentation today. First, I will introduce the background and the motivation of this paper. Next is proposed code designs. After that, I will introduce implementation and evaluation setups and experimental results. In the end, this talk is closed with a conclusion and a discussion. First, let me introduce the background and the motivation. I will introduce the cloud-native computing and its implications as the background, followed by the motivation of this paper. First, the recent shift in the production cloud environment from monolithic design to microservice-based architecture implies the prosperity of cloud-native computing. Let's see the fundamentals of cloud-native infrastructure. The first sign is a shift from a monolithic design to a single concern loosely coupled microservices. Those microservices are densely deployed at the physical virtual machines, containers, or referred to as a host in this paper. Whereas applications, for example, e-commerce, financial transactions, operate at disposable and immutable underlying system. We observed that such infrastructure has several implications. First, each microservice has much stricter quality of service or QoS requirements, since they are chained together to serve users. However, the environment is highly resource constrained because to lower the long-term capital expense, the cloud providers adopt mixed deployment of services and fine-grained resource allocation. For example, Zhuo reports that more than 90% virtual machines have only 1 to 4 CPU cores. Also, each host has massive metrics with rapid variations, including the upper-layer application metrics and the fundamental system metrics, which are monitored via specialized monitoring system to ensure the service level agreement. These implications pose several challenges to the cloud-native monitoring. As shown in this slide, a traditional monitoring system is deployed together with services. However, inevitably cause resource contentions with services running at the same host. The monitor occupies host CPU to collect, process, and upload metrics via kernel stack. We observe 2 kinds of mutual interference between service and monitor. First, enabling monitors cause jitters of online service especially during shopping festivals with high loads, because monitor and service processes may be scheduled to the same CPU core with CPU bonding or with default CPU scheduling policy. Second, the monitor process may be blocked when CPU quota is limited, or requesting monitoring metrics where the busy service interface. For example, a Redis application exports its metrics where the same interface as a service. However, assigning a dedicated call or interface for monitoring may avoid such interference. However, still cause large capital expense with CPU overhead. We further elaborate such mutual interference in the real deployment. In the left figure, the key-value store service Redis is interfered by the net data monitor. We can observe that both throughput and latency jitters in each monitoring cycle, the net data process is scheduled. In the right figure, we observe another kind of interference that the monitoring latency of net data or Prometheus jitters due to the high loads of small CPU quota of the monitored host. To avoid resource contentions and ensure quality of service monitoring, we propose the zero overhead monitoring system, or zero for short. The key idea is decoupling monitor from the monitored infrastructure, which is feasible from two aspects. First, we observe that most of metrics counters updated at fixed memory region, and the processes of raw metrics is simple and reproducible algebraic calculations. For example, generally the percipient counters are summed together to obtain the final counters. Second, RDMA is commonly supported in the state of the art cloud or data centers. RDMA enables both CPU and kernel bypass with one-sided operation, for example, write or read. So as a result, Zero can perform RDMA read on the registered memory region to collect raw metrics. The whole process is independent of the monitored host. Next is a core design of the Zero monitoring system. This figure gives the overview of Zero framework. We designed Zero to mainly resolve three challenges. First, we observe that most of the CPU time of traditional monitor are spent on collecting metrics from system or application processes. Zero also needs to eliminate such overhead besides the uploading overhead offloaded to RDMA NIC. Second, each controller collect metrics from multi-host or many QP connections in a large-scale distributed monitoring. However, it may cause a cluster problem. Third, the controller is also bottlenecked on CPU besides the network, as all collecting, processing, and uploading processes are offloaded to the remote controller. So Zero proposed the novel control and data plane design to resolve challenge 1. Introduce receiver-driven congestion control or flow control to resolve challenge 2, and incorporate efficient threading and I/O model to resolve challenge 3. First, I will introduce the control plane and the data plane of Zero framework. The control plane provides universal interface for application or system to register their metrics and update the corresponding metadata in the control region. Note that such registration overhead is disposable for system metrics and metrics of persistent or title service, because those services will run for a long time after registrated. For serverless computing, Zero further use RDMA write to update metadata. Specifically, once the metadata is updated, Zero use RDMA write to update the metadata of their metrics. As a result, the remote controller can read raw metrics with only one RTT, where RDMA read. The control plane also manage and share QP connection for all metrics at the same host to achieve largest scalability in the reliable connection or RC mode. Next is the data plane. At the data plane, Zero excessively adopt shared memory to avoid any CPU involvement for memory copy. Besides, we also observe that the metrics are distributed non-continuous in the memory space of kernel or application. So Zero also provides a memory management interface to aggregate metrics to continuous memory region. As a result, for each instance, Zero only needs to record one memory region entry and perform one RDMA read to acquire all metrics. To support large-scale distributed monitoring, Zero adopt a thread dispatching model. First, only one or two collecting thread is used to post RDMA read request, then polling compilations on multi-QPs in parallel. Because both post and polling operations are non-blocking. On the collecting thread, a receiver driving model is used to limit the total in-flight data of all connections where created. As a result, the build-up queue at switches can be controlled where the created. Currently, we determine the credit where the PFC or ECN threshold and the number of concurrent QP connections. We observe that such receiver drive model is efficient to avoiding cost with many connections and also guarantee the QoS level of the monitor itself. The accomplished requests are dispatched to a processing thread for further persistence and visualization. Next is implementation and evaluation setups and experimental results. We implement Zero framework and demonstrate its generality with 3 case studies, including Redis, Linux kernel, and eBPF metrics. This figure shows 2 types of memory management interface. We deploy Zero in 2 typical clusters. Virtualize the environment in the testing cluster and environmental environment with containerization in the public cloud. We evaluate Zero from CPU utilization at both agent and controller sides, monitoring latency and throughput. We also test Zero with different parameters, including sampling intervals, different number of instances, and a different number of hosts or connections. The sampling interval determines the monitoring quality of service, determine the QoS of monitoring, and the number of instances mainly impact the size of metrics, and the number of hosts shows the scalability of Zero. We compare Zero with legacy tools in our cloud and the state-of-the-art monitor used by large cloud providers, for example, NetData. And we also use Zero RPC implement with where the RDMA sent and receive as a baseline. This table summarizes the overhead of Zero in 3 case studies. First, we observe that the overhead of control plane is disposable because it's not affected by the sampling interval, as shown in the first figure of Redis case. Also, the data plane has 0 ahead, as expected, because the agent process is blocked after all metrics are rejected. Besides, 0 also reduces latency by 1 to 2 order of magnitudes compared with the TCP baseline. Here we only present the details of Redis case. You can refer to our paper for more details of other case studies. This slide gives the results on a large-scale distributed monitoring. First, we observe that Zero achieves much higher throughput and lower latency compared with the traditional TCP baseline. Besides, it also avoid triggering incast and triggering PFC or ECN with credit-based flow control. Another benefit is lower CPU utilization without useless busy polling when congestion happens. As a comparison, a Zero achieve much stable quality of service in the whole collecting phase. In the left figure, we compare the credit flow control with simple bandwidth delay product-based flow control. We can observe that BDP-based flow control easily cause ECN marks and the severe throughput declines. Our credit flow control keeps a stable performance in the whole monitoring process. Here comes to the conclusion. In this paper, we proposed the zero-head monitoring for the first time to the best of our knowledge, which effectively explores one-sided RDMA operation or RDMA read, and designs the novel control and the data plane to achieve this goal. Zero also supports large-scale distributed monitoring via highly efficient threading and I/O model and the receiver-driven flow control. Next is a discussion of about our experience and future work. First, to achieve high scalability and availability, we adopt QP sharing and group switching policy. To achieve high availability, many standby controllers, at least 2 standby controllers, are used when main controller is down. Also, we observe that the receiver-driven model is helpful to avoid network interference. The traditional method usually adopt physical isolation, where different physical links. However, it may introduce high cost, and also they use lower priority queue at the switch. However, it will frequently cause packet loss and timeout, which cause severe performance degradation of RDMA system. As a comparison, we observe that the receiver-driven model is effective to avoid network interference by controlling the build-up queue at the switches. Also, compared with state-of-the-art congestion control mechanisms, we observe that existing CC mechanism at the data center aims to achieve equal bandwidth sharing, and they also rely on ECN or inter capability on switches. However, the receiver-driven CC simply use credit and didn't rely on any signal from switches because the receiver knows if the congestion happens. Another observation is that currently we use lower BTP. We just use small credit lower than BTP. Because the ECN or PFC threshold at the switch is small. In our future work, we will use a combined mechanism of pacing and credit to avoid congestion at switches and both at the end or NICs. And we also wish to extend our mechanism to general case. That's all. Thank you.